video, we're going to do a general overview of Unit 8 from AP Calculus AB on applications of integration. First, we have 8.1, where we're asked to find the average value of a function on a closed interval. So first, before we can discuss average value, we have to kind of remember the mean value theorem for integrals. So remember, we have this purple curve and we have the area underneath it represented by the definite integral from a to b of the function f of x dx. So f of x would be the purple curve, and we would be finding the definite integral to get the exact area. What the mean value theorem for integrals says is that there's a rectangle that has the exact same area as the area under the curve. It's as if the curve melts and flattens out. The height of this rectangle is what we call the average value. So really, when we think about this, for the rectangle, we would have its height, f of c, times the length of its base, which would be b minus a, or the width of the interval. That has to equal the exact area under the curve. So when we solve for f of c, the height of the rectangle, we end up arriving at our formula for how we get the average value. The average value of a function is 1 over b minus a, the length of the interval, times the definite integral from a to b. Really, what I like to think about when I see this, or average value, is sort of like a numerical average where we add up and divide by how many. Think of this as the integral over the interval, sort of like you're averaging out the area. So in a real world application, here we have, I'm from Minnesota, we have the Minnesota Department of Health here graph for new hospital admissions with COVID. And if you kind of take the discrete graph and connect it with that yellow curve, the average value would be the height of the rectangle that would have the same area as that under the curve. So imagine balancing that out or melting it down so that there's a rectangle with the same area. The height of that rectangle would be at, I don't know, probably around 100 over there on the left axis, and that would be the average value. So sometimes you're asked to just find it with an explicit function. In this case, w of x equals cosine 4x over the interval from 0 to pi over 3. When it says find the average value, that's just using the formula. And again, this video isn't intended as your initial teaching. This is simply as an overview and a review to kind of collect everything together before an exam. So I won't be solving these problems. I'll be discussing their setups. Again, you can get further notes in your course videos, in AP Classroom videos. This is just an overview. So if we did 1 over b minus a, the average value of the integral, we would do 1 over pi thirds minus 0 times the integral from 0 to pi thirds of the function of which we're averaging, or finding the average value of, which in this case is cosine 4x. And then you would integrate accordingly. Sometimes on FRQs you might see, like this one, a piecewise function, and it says to find the average value of f on the interval from -1 to 1. So we'd first have to go from -1 to 0 plus from 0 to 1, but we'd still use our average value formula. Here we have average value embedded in a particle motion FRQ, where it says find in part B the average velocity. The minute I see average, I think average what? And it's velocity. So when I do the average value of f, I do 1 over b minus a times the definite integral of f. So this would be 1 over b minus a, in this case 6 minus 0, times the definite integral from 0 to 6 of the function of which you're averaging, which in this case is the velocity function. So you could enter that on your calculator. You can bring it in with your VARs, but again, don't make the biggest mistake. This is the value. We want the average value. So this over on the right-hand side, I would need to take 1/6 of it. Again, it's the integral divided by the interval. After that, we moved into connecting position and velocity, which we'd already discussed in another unit, but we applied some integration with it, and we came up with everything that we had to know back in our other chapters when we were doing derivatives and how they apply to particle motion. We added some integration because when we integrate, we remove a rate. So when we integrate velocity, think feet per second, we remove the per second and we get back to just feet. So the antiderivative, or when we integrate velocity, we get a position model. So we have three new little formulas here that I wouldn't suggest memorizing. You should understand them. When we do a total distance traveled, we would say, well, in miles. We'd have a position label. So if we're given velocity, we need to go back and integrate that. The reason we need the absolute value bars is because when we go backwards, we're still covering distance, and we want that to count, kind of like on the odometer of your car. Just because you go back home and your velocity is in the opposite direction as when you went to school, you're still accumulating miles. So we want all those negative velocities to attribute to our accumulated distance traveled. But when it says displacement, that's where we are from the start, or the net distance traveled. For those, we want those negatives to send us back. So that's why we don't have the absolute value. We then moved on to accumulation in applied context, section 8.3. And here's an example of that. Now we've been asked a bunch of questions that involve derivatives about a tabular situation like this, but some questions that involve integration can also be asked, because remember, when we integrate, we remove a rate. So when we have hundreds of entries per hour, right? When we integrate, we remove a rate. So we could actually do trapezoidal rule on this. We could do left Riemann sums, right Riemann sums. We could do the average number of entries during the day using our average value. Let's talk about that. The average number of entries per day in hundreds. The minute I say average of what? Entries. Average value of E of t. So I would do 1 over b minus a, 1 over 8 minus 0, or 1/8, dividing by that time interval, the definite integral from 0 to 8 of e of t dt, and that would represent the average number of entries. Then we moved on into finding the area between curves. We did it both with dx and dy. So let's talk about that. Here I have a curve f of x, and I have some area underneath the curve from a to b that I've got highlighted here in a nice bright pink. How do we get the area between two curves? When it was between a curve and the x-axis, we just integrated f of x dx. We were adding up an infinite number of rectangles. We're still going to be adding up an infinite number of rectangles. So the difference is our bottom function doesn't have to be y equals 0 or the x-axis. So let's talk about when it's not. So suppose we have an upper function, or f of x, and another function, g of x. And suppose we're integrating from a to b. You can see f of x is greater than or equal to g of x on that interval. I can still find the area, and I'm still going to be working with that rectangle right there. I still need its height. Again, that's one of an infinite number of rectangles that spread across to color that in green. So to get its height, we would have to do the top function minus the bottom function. Its width is dx. So that brings us to our formula, sort of. You just need to understand it. We're just adding up a bunch of rectangles. We're going to be doing f of x minus g of x, but be careful because it's really not always f or always g. It's the top function minus the bottom function. That gives us the height of all the rectangles. The dx gives us their width, or dy if that's the case. So here we have two functions crossing, one in blue and one in red, and they're labeled. If I were asked to find the area between these curves, well, I'd start on the left here and I'd think of coloring, top minus bottom. I'm coloring on all the pink, and this blue function's on top the whole way. So I would just do the blue function, 2x the cubic, minus the quadratic to get the height of the rectangles. Dx would be their base. But the minute I hit 0, the top and bottom functions swap. So don't forget, you have to swap them in your integral. So that from 0 out to 2, we'd be integrating from 0 to 2, and then we'd have the quadratic, x squared plus 3x minus the cubic, dx. So be careful if those functions cross. So suppose you had to set up an integral to find that yellow region, the area between those two curves. We would do top function minus bottom function. I like to write it as a single integral. And the top function is the red one, or x squared plus 1, on my entire sweep from left to right. So I'm integrating 0 to 1 across the x-axis. My function of x is top function minus bottom function, and then dx. Again, if we're doing dy, we took a whole bunch of notes on that as well, we would be climbing up the y-axis, functions of y, dy, and instead of top minus bottom, we did right minus left. But then we just do our antiderivatives. If you need it, that shouldn't be anything you need to really look at. So suppose you needed to set up an integral for the area between these two quadratics, and it wasn't graphed for you. And maybe it wasn't calculator active. You would have to know how to graph those two, so make sure you know how to do that. Then remember, we do top function, which in this case is the blue one, 2x minus x squared, minus the bottom function, dx. And again, they never swap out, so I can sweep across the x-axis with one integral. Now, if I had done dy and colored up the y-axis, I would have to go to y, from y intersection up to y intersection, and I'd do the right function, which is now the red one, but I'd have to solve it for y. So it'd actually be x equals root y minus, and I'd have to solve over here for a function of y. So x as a function of y, and then right minus left. Here it shows up in the 2013 AP free response question number 5, and we have part A. We have two functions. We were non-calculator active, so we have to know that the quadratic that opens up is f, and that's actually the lower function. So remember, it's not always f minus g, it's top minus bottom. All right, it's not or right minus left if it was dy. These are functions of x though, which makes me feel good. My cosine function, or g, is on the top. When it says to find the area, I'm thinking of coloring from 0 to 2 with an infinite number of vertically made rectangles where their heights are top, g of x, minus bottom, f of x. Their width is dx. So I'd integrate from 0 to 2, sweep across the x-axis. G of x minus f of x would be my integrand, dx, and my limits would also be for x from 0 to 2. Be prepared, again, to have to sketch them to determine their intersections and whether top and bottom swap out along the way. So be prepared in multiple choice to not always have that calculator available. After we did area, we moved into volume, and we started off with volumes with known cross sections. We need to be comfortable with the models for the squares, the rectangles, triangles, and semicircles. So let's get a general idea. Again, bring back this picture that we had in class. Suppose this was in maybe that red function, the square root, and maybe the blue is x squared. We picture laying that flat on the table, and we have as what's actually called a z-axis that's coming up off of your paper. I talked about it as being a bread loaf pan, and you pour the batter in and it bakes up off the bread loaf pan, and it makes a shape of bread where when you cut it, you know what the slices look like. In this case, I'd be handing all of you a square slice of bread. All right, but what would the volume of the whole loaf be? I'd obviously need to add up all of your slices, technically an infinite number of them. but they all have a side length of top minus bottom, which we called S. So S is really important, that chord that cuts between the two functions. Again, top function minus bottom, unless we're going perpendicular to the y-axis, then we do right minus left. Here we have building up off of with isosceles right triangles with a leg across the base. Well, first let's talk about this square. The area of a square is side times side, so I'd have S squared, again where S is top function minus bottom function, and its depth is dx. So we always do an area of a face. If it's a square, it's just side times side, and then dx. If it's the isosceles right triangle with the leg across the base, you can see that's half the square. So that's why with our model we did 1/2 the definite integral of S squared dx. So for all of them we do the area of a face times the depth. Semicircles, the same thing. You just have to remember the multipliers out front for these geometric shapes, and that's in your notes. But remember the integrand always had an S squared. If it's just a square, that's all it was. If it was the isosceles with the leg across a base, like on this figure here in yellow, then it was 1/2 S squared dx. With the hypotenuse across the base, it was 1/4 S squared dx. With the semicircles, it was pi eighths. And I said, think of I ate pie. All right? In a circular pan. So semicircular is pi eighths multiplier out front. Don't see equal out of triangles much, but that's root 3/4. It's good to commit those to memory, even though we derived them all in class, but it all has to do with the area of the face, which we call A of x, times the depth. Those are your 3 dimensions for your volume model. Again, this area almost always, except in the case of the rectangle, where they tell you like it has a constant height of 3. Well, then we would just have S times 3. But for all those others, there's an S squared in the integrand. So here's where this appears in that same FRQ. It was part C, and it says, now there's your bread loaf pan, the base of your solid. It's going to be laid flat on the table. We're going to bake it up or build up off of it so that when we cut slices, you get a square. So the first thing we do is drop that chord down. It says perpendicular to the x-axis, so we go thank you, right? And we picture building up squares. Well, how do you get the area of a square? Side times side. How do I get that yellow side? Top function minus bottom function. Remember that top function was g. So g of x minus f of x is my side. I would do g of x minus f of x quantity squared. It's my 2 dimensions. Dx is my third, from 0 to 2. If it said semicircles, pi eighths, the definite integral, from 0 to 2 of side squared, dx. If it said isosceles right triangles with the leg across the base, half of the squares. So 1/2 S squared dx. All right, then we moved on into volumes by what I call revolution, or volumes with discs and washers. And we did both x and y axis. So here's a visual, first of all, of the washer situation. So suppose I revolve that top curve around this horizontal axis. Let's call it the x-axis. And I look at one of the circular cross sections. Remember, there's an infinite amount and their depth is all approaching 0, but we have to slice out a finite one to look at its dimensions. It becomes a cylinder, a really, really, really shallow cylinder, but its depth is a little change in the x-axis, or dx. So we're focusing on one of those. So revolving that purple function around that horizontal x-axis, when I slice, I'll get all of these circular cross sections. And because I'm butting up against the axis of rotation, they'll be solid disks. They're cylinders. Pi r squared, h. And what's r? The distance from the axis to the curve. So here we have a model for how we find the volume when we do horizontal versus the volume when we do a vertical axis of revolution. Sometimes we have washers where there's a hollow hole cut out. So if you were to picture this, we would do pi times big R squared minus little r squared. Basically, that subtraction is cutting out the inner cylindrical hole. Okay, and again, if we do dy, we dealt with that in class, that it's the same model, we just need to get all things in terms of y. The integrand, the differential, and don't forget the limits. And instead of doing top minus bottom, we do right minus left. Now suppose we were revolving this around that dotted red line up there. It's horizontal. Let's suppose it's the line y equals 4. Well, what's my big R? We always draw it perpendicular to the axis of rotation is how we draw our representative rectangle. So there we are, perpendicular to the axis of rotation. We always do top function minus bottom function. So in this case, my top function would be the horizontal line. I would do 4 minus the equation for the bottom function for my big radius. My little radius is axis to the inner edge of the curve. Top, which in this case is the axis, minus bottom, which in this case is the function for the top part of that region. So we do pi times big R squared minus little r squared in our integrand. Be careful you don't do big R minus little r quantitatively squared. That's a pretty common mistake. So let's go take a look here at a visual that I got off of YouTube. So let's turn volume through it. What we've got. This is the line y equals the square root of x, or the function, and a line y equals 1/10, also being bound by x equals 4. I've shaded in the red region. We revolve around the axis. You can see three-dimensionally that that's going to make a solid that's got a hole drilled out of it. So when we slice it and we take a look at it, we've got what's called a washer. A cylinder cut out of a cylinder. So we need the big radius and the little radius. The height is dx. So the big radius is axis to the outer edge of the curve, top minus bottom, or root x. The little one would be axis to the inner edge of the curve. And then we just do pi times big R squared minus little r squared. So again, back to 2013, AP free response number 5. In letter B, we were asked to write but not evaluate an integral expression that will give the volume when we revolve region R. Remember in part A, we found its area two-dimensionally. In part C, we built up off of it so that we had square cross sections and we did volume. And now in part B, we're going to take it and revolve it. And think of revolving and think of circles and cylinders. We would have a washer problem because when we draw a representative rectangle perpendicular to the axis of rotation, we have a hole in the middle. We don't butt up against the axis of rotation. So big R is axis to the outer edge, top, which is 4, minus bottom. And if you remember, the bottom function was f of x. So big R is 4 minus f of x. Little r is axis to the inner edge of the curve. Top, which is 4, minus bottom, which was g of x. So 4 minus g of x. So when we set up our integral, that will result in finding the volume of the solid when it's revolved around the horizontal line y equals 4. We have our pi out front. We have our definite integral from 0 to 2 sweeping across the x-axis. We do big R, 4 minus g of x, the yellow one, squared, minus little r, 4 minus f of x, the blue one, squared, dx. And you feel free to go look up the scoring guidelines on that. And again, this was just an overview of the whole chapter. If any of this you're like, that was way too fast, that means you need to go watch the full notes or hop on AP Classroom and watch some notes in there. All right, so best of luck. In that last part B, Remember that the bottom function was actually f. So I think I had them swapped in my narrative. So just make sure you would say it's 4 minus f of x quantity squared. All right, and then the inner function would be 4 minus g of x quantity squared. All right, so just a little fix on the narrative on that one. Have a good one.